In Chapter 9, we're going to look in more detail at the electrons. And the reason that we focus on electrons is electrons are the most important part of atoms if you're talking about chemical reactions. So to understand chemical reactions, we have to understand electrons. And it turns out that electrons have some property where they behave similar to waves. So for example, a wave of energy has a property called the wavelength, and wavelength is abbreviated with this Greek letter lambda. Lambda, the wavelength, is the distance between two identical points on the wave. So from the peak of the first to the peak of the second, that distance is the wavelength. So because we're talking about a distance, we will be measuring this in some form of meters. Could be nanometers, picometers, depending on how big or how small the wave is. The frequency is abbreviated with the letter nu, which looks like a V. And nu, or frequency, is how many waves pass by per some unit of time. So the numerator in this number of waves doesn't have any units. The denominator, time, will usually be measured in seconds. So nu, or frequency, has units of 1/seconds, which can be written as seconds to the -1 power, and both of those are also called hertz, capital HZ. And the wavelength and the frequency are related to each other by this formula that says the speed of the wave, we'll call that c, is equal to frequency times wavelength. And the waves that we're talking about in Chapter 9 are called electromagnetic radiation, which is things like red light, blue light, also infrared radiation, X-rays, radio waves. All of those are electromagnetic radiation, and the speed c is a constant for electromagnetic radiation. It's very fast, 3 × 10⁸ meters per second. So this diagram shows how the only difference between one form of electromagnetic radiation and another form is either the wavelength or the frequency. By this equation, if the wavelength changes, the frequency has to change. So on one end of this scale, we have things like radio waves, and at the other extreme we have X-rays and gamma rays. X-rays and gamma rays do a lot more damage. They have very high energy. On the other hand, radio waves are hitting us all the time and don't do any damage because they are very low energy. This blow-up shows the visible spectrum, which is what we can see with our sense of vision. We can only see from a wavelength of about 750 nanometers to 400 nanometers, which is this tiny little region of electromagnetic radiation. Notice in this formula, the speed is a constant equals frequency times wavelength. So if the wavelength gets smaller, the frequency has to get bigger. That's called an inverse relationship between wavelength and frequency. If one goes up, the other one has to go down. Also, the energy of the wave goes up as the frequency goes up. So energy and frequency rather are directly related or directly proportional to each other.